the text to image ratio here is not ideal, but let me walk through this, right? So this work concerns itself mostly with MS2, tandem mass spec, especially coming from liquid chromatography, mass spectrometry. And this is a nicely kind of constrained problem because we have ideally one molecule, right, whose structure is often unknown, kind of low concentration, and we want to figure out what is the structure we're dealing with here, right? So if I can kind of point your attention over to the left, there's an example kind of spectrum, and these are the features of a spectrum that you want to use to assemble kind of some information as to what might the molecular structure of this unknown molecule look like. And there are two kind of features we're interested in. The first is the spectrum peaks or the fragments, right? These are mass to charge ratio measurements of your molecule. And the second is the neutral losses, right? The mass to charge ratio differences between these fragments. Now, a little while back, a couple of folks, introduced this idea that using topic modeling approaches, borrowed from natural language processing, would be a nice way of capturing this kind of information in an MS2 spectrum in a very high throughput and kind of reliable manner, where you can take an MS2 spectrum, decompose it into these topics, and then these topics give you an idea of like reoccurring fragments and features, across different MS2 spectra. The problem, though, is that even though this mimics what people do by hand very well, it's an unsupervised method. So then you are kind of stuck trying to figure out what these topics mean in chemical space, even though you have that kind of feature composition. That's very time intensive, labor intensive, and that's kind of unreliable. So what this work is doing is trying to move a step further and add a supervised dimension to this kind of approach. So we're using a more recent topic model that's labeled latent Dirichlet allocation. And now we're looking over here in the center, where what we're adding is a layer of supervision. So you, the user, can now decide, look, these are the chemical substructures I'm really interested in labeling. I want to know if these structures are present in my new MS2 spectrum. Given kind of a training corpus of labeled MS2 spectra, whose structure you do know, and therefore you have, your substructure labels, you can then still do a topic decomposition in the same way where you get probability scores for each one of your topics for your new unknown spectrum. And you can look at the featured composition of these topics. The additional kind of benefit here is that now you don't have to go through all that work. You can take a look and say, look, these are direct scores for each one of these substructures. And now I've assigned a good prediction for each one of these substructures. And if I hand you those and you're an expert chemist, or maybe you want to stitch that together in some other way, you can take these different substructure pieces and piece them together in a way that you have a good kind of guess as to what the structure corresponding to that MS2 spectrum might be, or at least a very finite number of structural candidates. And then you can synthesize your standards, run them on MS2, and verify. And so over on the right, this is what this looks like in practice. We have an example MS2 spectra from the benchmark data we've been using. These are mostly publicly available MS2 spectra. There's the parent molecule, and in red, we're showing the kind of most highly scoring, the top recommended substructure. We know its structure because it's a supervised model. In addition to that, because it's a topic model, we know the feature composition of the top recommended structure, both in terms of the spectrum shown in red, and also right below in that table, literally in terms of the spectrum features, the fragments and the losses that are responsible for that prediction. More recently, what we've been doing, and something we're excited about, is kind of stress testing this sort of model and taking a look at how this kind of model prediction performs in increasingly kind of difficult test spectra. And so, I think the important dimension to look at here on that bottom plot on the right is moving from right to left. What we're looking at is increasingly kind of difficult subsets of training spectra that correspond to very chemically different molecules from the training spectra. And what we're seeing is performance compared to kind of a standard baseline K nearest neighbor model, corresponding to what a database search might produce. And as we go from kind of bottom to top, we're looking at increasing relative performance of this kind of topic modeling approach compared to a baseline and this kind of stress testing. So let me stop there. Happy to take any questions on this. Please do shoot me a line if you have questions later too. My email is on the slide as well. And big thank you to the collaborators, especially the ones listed on the poster.
Thank you, Gabriel. Very interesting work. Again, if you have any questions, just unmute yourself, ask your question, or you can put it in the chat if you prefer. If we don't have any questions now, if any questions come up later, please feel free also to. I posted the link in the chat, and the poster presentations are visible in the app, so you can also directly connect. All right, thank you so much again, Gabriel, and we'll move on next and today's virtual poster session. Andrew